So here's a variation of the last problem. We still have the observer being 300 meters from the launch pad. The rocket's still ascending vertically at a rate of 60 meters per second. But now we want to find the rate of change of the angle between the ground and the observer's line of sight when the rocket is 400 meters high. So there's going to be a lot of repeated information as in the problem 3A, but we'll go through the same process. We have that circling our key numbers that we've got the observer is 300 meters from the launch pad, descending 60 meters per second, 400 meters high. Those are our key numbers. Our question being asked is find the rate of change of the angle between the ground and the observer's line of sight. So here's our question. And then boxing our math terms. Again, we have distance, so that's from the launch pad. That's going to give rise to a variable. It's ascending vertically at a rate, so that's our derivative. We want to find the rate of change of the angle between the ground and the observer's line of sight. So there's all our key ideas. We have, I'm going to bring over the picture from the last problem. We still have the observer. She's 300 meters from the rockets, ascending vertically. But now our variables have changed a little bit. Before, we were interested in this distance. But now we want to know the rate of change of the angle. So we still have the rocket ascending vertically, and we want to know the rate of change, and we'll call this, say, theta. So y is still a height of rocket, and our theta, though, is our angle of elevation. So theta is the angle of elevation. So that's what theta is. We know that dy dt is still 60, so dy dt is still 60. And we want to know what is the change in that angle. What is d theta dt when y is equal to 400? So we're looking at the rate of change of a different variable from the last problem. So what is the rate of change? So as the rocket goes up, this angle is increasing. So it should be positive. And we know that dy dx, or dy dt, sorry, is 60 meters per second. Okay. So what is the so we've organized, and now we need to relate our variables. So what is the relationship between theta and y? Well, we still have a right triangle, and there's an angle, so we have our trigonometric identities. And since we've got the opposite side as one variable and the adjacent side is a constant, that tells us that probably the trig function that's best used here would be tangent, right? Because tangent is the ratio of opposite over adjacent. So the relationship we'll use is that tangent of theta is equal to the ratio of opposite over adjacent, or y over 300. Right? So that's our relationship. And what is the approach we're going to use? Well, this is a related rates problem, so we're going to use implicit differentiation. to solve the problem. Okay, so give ourselves some room here. Here's the problem. Tan theta is equal to y over 300. We know dy dt. We want to know d theta dt. So we're going to use implicit differentiation to get our expression we're using for. So differentiating both sides, I see that the differential of tan theta has to be equal to the differential of y over 300. Well, the differential of tan theta is secant squared theta, or the derivative of tan theta is secant squared theta. So the differential is going to be secant squared theta d theta is equal to the differential of y over 300. It's tempting to think that this is a quotient rule, but remember y divided by 300 is just, because I see this too often, I'm going to write it out very slowly, right? 1 over 300 times y, right? That's y divided by 300. So this is really a constant, so this is 1 over 300 dy. That's what our differentials are. Going back, and what do we want to know? Well, we want to know d theta dt. And so this tells us that we should be dividing through by the denominator here, dt. So we divide this side by dt, and we divide this side by dt, arriving at the equation that secant squared of theta d theta dt is equal to 1 over 300 dy dt. But we know that dy dt is equal to 60, right? This says that they're the same. So dy dt comes right here. And so giving us that secant squared of theta d theta dt and since dy dt is 60 and 60 over 300 is 1/5, and so finally I can divide both sides by secant squared, and so I get, and then using my trig identities, right? So 1 over secant squared is just cosine squared. So I get that d theta dt is equal to 1/5 cosine squared of theta. So that's my relationship for d theta dt. And I want to know, what is d theta dt when y equals 400? Well, my gosh, I don't even have a single y in this equation. But I know my my trig identities, my relationships, so I could figure out what cosine squared is when y is equal to 400. So over here, I'm going to make a little bit of side work. So I want to know, what is cosine squared of theta equal to when y is equal to 400? Well, I've got my triangle. And so now this side is 300. This side is 400. Here's our angle theta. And cosine is all about the ratio of adjacent to hypotenuse. So I need to know, what is the hypotenuse here? We worked it out in the last problem, actually, and you may be able to recognize that this is related to a 3, 4, 5 triangle. So, but you could use Pythagorean's theorem to solve and find that length of the hypotenuse, when the base is 300 and the height is 400, has got to be 500. This tells me that cosine of theta is the ratio of adjacent to hypotenuse, so it's equal to 300 divided by 500, which is equal to 3/5. And so finally, what is cosine squared theta? Cosine squared theta is equal to 9/25. And so finally, we can answer the problem. We want to know d theta dt when y is 400. So d theta dt when y is equal to 400 is equal to 1/5 times, well, cosine squared theta, but we just found cosine squared theta when y is 400 is equal to 9/25. So this is 9/25, and that's equal to 9/125. And the question here is, what are our units? Notice that d theta dt is all, there is no dy dt's or anything. I mean, it's if we worked it out very closely, we would see that everything cancels. But we know that dt is a rate of time, so that's going to be seconds, and theta will be measured in radians. So this is equal to, not equal to, but when we put our units on, that the units will be radians per second. So the angle is changing at 9/125 radians per second. And again, we've solved it, and we should check our answer, that at least that it makes sense. And coming back here, if the rocket is ascending, the angle is increasing, so the rate should be positive, and sure enough, we get a positive sign. So at least signs make sense, our units have made sense, so assuming we didn't make any errors, then this should be our answer. And we would write this out as addressing this question, that the rate of change of the angle between the ground and the observer when the rocket is 400 meters high is 9/125 radians per second.